Hey all, I'm going to go through the first 6 topics within Unit 7 in this flipped format because they are quite simple to understand with some basic background information so we can focus our class time on doing some application problems. Unit 7 is our Introduction to Equilibrium. Equilibrium is a topic in chemistry that will be discussed in Unit 7, 8, and 9, the part of 9 that we haven't done yet. So Unit 7 is our Introduction to Equilibrium and topic 7.1 specifically. So the key for all of the videos you're going to be watching in this segment on 7.1 to 7.6 is that some reactions can occur in both forward and reverse reactions, sometimes proceeding in each direction simultaneously. For this particular short introductory section, you'll be able to explain the relationship between the occurrence of a reversible chemical or physical process and the establishment of equilibrium to experimental observations. This is the key information from the College Board. Many observable processes are reversible. Examples include evaporation and condensation of water. So anytime you have a phase change, all phase changes are physical equilibrium systems. Right? You have the presence, you have the, during a phase change at a specific temperature, you have the conversion from one phase to another and back again. For chemical dissolution or precipitation of a salt, this is when you have a saturated solution. Saturated solutions are physical equilibrium systems where the rate of dissolving is equal to the rate of crystallization. And then we'll talk mostly in this course about chemical equilibrium system. The rest of the essential knowledge pieces right here, we will talk about in the notes. So when you're dealing with a chemical equilibrium system, you have a reversible reaction. You have a chemical reaction in which products can react to reform reactants. You're going to have that double arrow system. So when you're dealing with an equilibrium system, the rate of the forward reaction, this is so important. The rate of the forward reaction equals the rate of the reverse reaction, and the concentrations remain unchanged. The concentrations do not have to be equal to each other at equilibrium. They just have to be maintained at equilibrium. Whenever you see an arrow going in both directions, you know your system's in equilibrium. This graph is showing you rates of the changes in concentrations of two substances versus time. And we looked at this when we did kinetics, right? When you have the rates equal to each other, the rates are equal to each other of the forward and reverse reaction, that at this time we've established equilibrium in the system. So we have the N2O4 converting to NO2s at the same rate the NO2s are converting back to N2O4s. So it's really important that you understand the difference between the rate stability and the concentration stability. So at equilibrium, rates are equal, but concentrations are constant. So when you look at a system at equilibrium, it may appear to not be changing at all, but in reality, it's extremely dynamic. Okay, equilibrium is not a static situation. It's a constantly dynamic. So macroscopically, to your eye, you might not notice a change, but microscopically, you have the conversion of reactants to products and products to reactants at equal rates. So it does not appear that a change is occurring. So kind of like this picture where we have water pouring into a container at the same rate that water is flowing out of the container, so the level of water in the container remains constant. That's a really simple example, but it works. So that's 7.1, is just understanding that rates are equal and concentrations are constant when you have a state of equilibrium. Topic 7.2 just goes briefly into the direction of reversible reactions. So for this section, you'll be able to explain the relationship between the direction in which a reversible reaction proceeds and the relative rates of the forward and reverse reaction. So we're going to look at some graphs here, very similar to the kinetics graphs we did in Unit 5. Let's see. If the rate of the forward reaction is greater than reverse reaction, then you're going to overall be converting reactants to products. If the rate of the reverse reaction is greater than the forward reaction, then there's a net conversion of products to reactants. At equilibrium, that's when your rates are equal. So again, it's reinforcing that idea. And we have a graph like this again. So the rate of the forward reaction, and now it makes sense that if you're starting with a lot of reactant that you're trying to convert into product, that the initial rate of the forward reaction would be very high because you just have reactants in your system. And the initial rate of the reverse reaction would be 0 because we don't have any products yet. But as reactants are used up, that forward reaction will slow down. And as product is created, the rate of the reverse reaction will speed up. Now, eventually, under certain conditions, the two rates will equalize and you have a system that's at equilibrium. Now, this graph is different. Look at the axes. The axis on this graph is rate versus time. The axis on this graph is concentration versus time. So this is very similar to what we looked at in the kinetics unit. Okay, so we were measuring the initial rates of reaction because as reactions proceed, you might not have that obvious differences in the reaction rates. You have these steep slopes initially, okay? And again, remember from kinetics that the differences in the curves are based on the stoichiometry of the substances. So you can see here that the nitrogen monoxide and nitrogen dioxide perfectly mirror one another because they are stoichiometrically equivalent. Ooh, words. And the oxygen product increases in concentration half as rapidly as the nitrogen monoxide does because stoichiometrically it is produced at half the quantity. Now, moving on from this graph, if we extend it, you can see here beautifully that once those lines level off, we have reached equilibrium at that particular time. How do I know? Those lines aren't touching each other. How do I know that's equilibrium? Because at equilibrium, the concentrations are constant. They're not equal to each other, obviously. They could be. Mathematically, they could end up all overlapping, right? And there's calculations we're going to be doing that you might end up with numbers that are, you know, they all meet and they level off together, but it doesn't have to be the case. What must be the case is the concentrations must remain constant. So these Y values that I'm marking in red here, those Y values wouldn't be equal to one another, but they are maintained. Why are they maintained? Because the rate of reaction is the change in concentration over change in time. We have no change in concentration as the time is proceeding. So those rates are equal. It means the same thing. Here's just another example of that concentration versus time. You see the differences in the curves based on the stoichiometry of the reaction, but you would be able to draw a vertical line, you know, approximating when equilibrium is established. So that's 7.2. That is going to be the end of the first video. I'm going to do 7.3 and 7.4 separately for you. Bye.